Hello everybody. In the previous classes, we have got introduced to flip-flops. So, we have seen clock flip-flop, edge-triggered flip-flop, and we had seen representation of flip-flop in the form of truth table. So, we shall look at some other representation of flip-flop in this particular class, which will be useful for analysis of sequential logic circuit and synthesis of sequential logic circuit, which will come up in future classes. So, we start with SR flip-flop, and what we discuss now is representation through characteristic equation. So, truth table of SR flip-flop we had seen before in a compact form like this and more elaborate form which can be represented here. Okay. So, this truth table is also called characteristic table in some of the literature. So, if we remember that for S and R, when input are 0 and 0, then if current state is 0, next state will also be 0. Current state is 1, next state will also be 1. That is, previous state is retained. Okay. If inputs are 0 and 1, okay, then the flip flop will be reset irrespective of what had been the previous state. So, whether it is 0 or 1, next state is 0 and 0. So, this is the case we have seen in a more compact representation. When it is 1 0, it will be set irrespective of the previous value, it is 1. Okay. So, this is the case in more compact representation, and when it is 1 1, it is not allowed, 1 1 is not allowed. Okay. So, if you want to get a characteristic equation that represents this flip flop, what we will do? So, this is the current value based on which the next one is obtained. So, we form a Carnot map, or any other minimization technique also is useful. So, the idea here is we want to represent Qn plus 1, okay, as a function of S, R and Qn, that is the idea. Okay. So, we can take min term based representation and then we can minimize it using Boolean algebra or any other technique. So, Carnot map is handy. So, we look at the Carnot map based representation of this logic equation, right. So, SR 0 0, if Qn is 0, then the Qn plus 1 is 0, 1, Qn plus 1 is 1. If it is 0 1, it is reset. So, 0 0, if it is 1 0, it is set, okay, and 1 1. Since it is not allowed, we put a don't care here. That means from the equation whether we get it 0 or 1, it does not matter, because the value will never appear at the SR flip flop input, a case of both being 1, right. So, we shall use that don't care either as 0 or as 1 depending on how the groupings can be obtained and a minimized representation can be made available. Okay. So, for this case what we see, the largest group of these ones that can be covered is coming where these don't cares are included, and for that we see that S is remaining constant with a value of 1. So, what will be coming here? S will come as one of the product term. I mean, there is no other term which is getting ANDed with it, and this one is not covered, this one is already covered, but together we can form a larger group, okay, group size of 2, in which we can see that R is 0 here, R is 0 here. So, the variable that will be coming here is R bar, one term, one literal, and the other one is Qn is remaining constant with a value 1. So, Qn will be coming for this one. Okay. So, then we sum it up and we get Qn plus 1 represented as S plus R bar Qn. Okay. So, this is the characteristic equation of SR flip flop. Is it clear? Right. So, next we look at characteristic equation of JK flip flop, right. So, characteristic equation of JK flip flop, again we shall start with the truth table. So, truth table with J, K and Qn, these are current value based on which the future value will be coming at the next clock trigger, and when we try to represent again similarly as a function of j, k and qn, right. So, we would like to have a Karnaugh map based representation first, and then we shall see how to get a minimized representation, right. So, how SR flip-flop and JK flip-flop truth table differ or characteristic table differ. So, up to this 0 0 input, okay, 0 1 input and 1 0 input, they are the same, right. So, 0 0 qn, 0 1 0, 1 0 1. So, only place where it differ is 1 and 1, right. So, when 1 1 is presented as input in SR flip-flop, it is not allowed. In JK flip-flop, the output, the next state toggles. That means, whatever has been the previous state 0, it becomes 1, and if it was 1, it becomes 0. So, that is what you have seen over here in a more compact representation. So, for getting the minimized representation in the Karnaugh map, so 0 0, 0 1 and 1 0 will be having same entry as that of SR flip-flop, okay, and we can get it directly from the truth table also, right. For 1 1, now we have got a different entry. Earlier it was not allowed, so we put don't care, right. Here, if it is 0, if it is 1 1, then next value will be 1, and if it is 1, next value will be 0, right. This is understood. So, with this we go ahead with the minimized expression. How to find the minimized expression? We know, the again forming the larger group possible, and we have to cover all the ones if we are looking for SOP representation, right. So, this is one group which is covering this 2 1, and this is another group which is covering this 2 1. And what we see here, that qn is remaining constant with 0 and j is remaining constant with 1. So, j qn bar will be one product term that is coming, and which will represent this group, and this group will be represented by similar to what we had seen in the previous case. So, this is your k remaining with 0. So, k bar and qn is with 1. So, qn. So, these two product term, when you sum it up, you get the characteristic equation of JK flip-flop. Fine. Clear? Okay. This input is just pushed to their next state, right. And if 1 1 is presented, right, so the output will become 1 1 irrespective of what is the previous previous state. Okay, the next state will be 1 1, right. So, when we put it into the form of a Karnaugh map, we have two variable. Okay, so 4 such entries will be required. So, for d is equal to 0, this is 0 and 0, right, irrespective of qn being 0 or 1, and d is equal to 1, this is 1 and 1, irrespective of qn being 0 or 1. Okay. So, in this case, we have only one particular product term coming out of this, because only one group is sufficient to cover both the ones, right, and for which d is remaining value, d is having a value with 1, right. So, qn plus 1 is simply d. Okay. So, it is just the, so this is the characteristic equation of d flip-flop. Clear? So, here we introduce another flip-flop, okay, which we call T flip-flop or toggle flip-flop, right. So, basically if we try to visualize what would be the internal circuit of logic circuit of T flip-flop, then we refer to how JK flip-flop is made, okay. And then if we connect both the inputs of J and K and tie together, remember between SR and D we had an inverter, here there is no inverter, okay. From SR to D we had put S as D and then R was D inverted, okay. So, there was a NOT gate, here there is no such NOT gate, directly it is connected. So, it becomes a single input flip-flop, right. So, all those things pushed inside the logic circuit within a particular group, okay, where all the elements are there, then what we get is a single input flip-flop. Of course, it is clocked, positive triggered and all, and the Q and Q bar, this is outside, that is why this bubble is there. If it is inside, the convention is not to put the bubble. I mean, these symbols Q and Q bar, if they come inside, bubble is not put. We have discussed this before, okay. So, this is your T flip-flop, okay. So, this T flip-flop, then what would be its truth table, right, or characteristic table. So, this is your if 0 is presented at the input, okay. So this is like j and k both being 0, 0. So previous state will be written. So if it is 0, it is 0, 1, it is 1, okay. And if 1 is presented, so it is like for jk flip flop both the inputs are 1 because t is equal to 1. So the output will toggle, right. The next state will become the invert of previous state. So 0 becomes 1, 1 becomes 0. Is it fine? Right. So if you try to get a characteristic equation out of it, the minimized expression, so we can see for t is equal to 0, the previous value is written. So 0 is 0, 1 is 1, okay, and t is equal to 1. So it just toggles. So 0 becomes 1 and 1 becomes 0. Is it okay? So now what we see that larger group of 1 is not possible, only one member groups are there. So this is one group and the other one is over here. So it is t, this is t and qn bar, right, and this is the other one is tn bar, this is 0 and qn. So this is your t flip flop characteristic equation. Is it okay? Right. So we shall make use of all these things later in subsequent classes. We shall see how to make use of it. Next is another representation through excitation table. Okay, this is interesting. While characteristic equation and characteristic table or truth table are useful for analyzing the circuit, excitation table and the one that is to follow, we shall discuss that also, that is useful, that are useful for synthesis, okay, design of circuit. So all those examples we shall take up in subsequent future classes. So right now we are learning how to represent flip flops in various forms, okay, through various representations, okay. So what excitation table tells us? So excitation, so what sort of excitation should be present at the input of the flip flop, right. So input of the flip flop is S and R for SR flip flop, right. Other one is clock. Clock is just simply triggering, and based on what is presented at S and R, the output changes, okay, the next state changes, and of course there would be reference to the previous state, feedback, etc., etc. That is another part of the story. Here the external excitation, external input that is there to trigger to make a change in the flip flop. That is what we are trying to figure out, okay. So in that in that context, so for SR flip flop, we are looking for excitation when we see that the previous state was 0 and next state is also 0, okay, current state to next state, right. So previous state was 0 and next state is also 0. If that is what we observe, then can we figure out what was the input at S and R? We can figure it out from the truth table. If previous value was 0 and next value is also 0, okay. So that means in one case we can see that previous state is written 0, 0, right. So previous value will be written. So we are talking about 0, previous value was 0 and next value is also 0. So it will occur when the previous, when the input is 0, 0, okay, that is possible. And instead of input is, input being 0, 0, if input was 0, 1, then also the next state will be 0. Please understand this part, okay. So if we refer back to more elaborate truth table of SR flip flop, okay. So we can see if this is 0, 1 and previous value is 0, next value is 0, and 0, 0, previous value is 0, next value is 0. So in both the cases it is happening, right. So if this is what is observed, we can say that either of 0, 0 or 0, 1 was presented at SR to make this happen, that it has changed from 0 to 0. And how we can represent it in more compact form? We can write this as 0x. X stands for don't care. So that means S need to be 0 and R could be any of 0 or 1, for which if the previous value was 0, next value for sure will be 0. Okay? This is what is coming as entry into the excitation table. So 0 to 0, you can see the input required to be is to be 0, 0 or 0, 1 in more compact form 0 cross 0x. Is it okay? Right? Now, what are the different possibilities of this transition? Because it is a 1 bit kind of thing, right? Flip-flop contains only 1 bit of information. So 0 to 0 is one possibility that we have already explored. So the other one is 0 to 1, 1 to 0 and 1 to 1, right? So in each of these cases, we can figure out if such transition does take place, then what has been the excitation at the SR input. So for 0 to 1, right? So the previous value was 0, next value is 1. So you can understand from the truth table that input required to be 1 and 0, it is becoming set. 0, 0 will not occur, will not help because previous value will be returned, right? So if you put 0, 0, then 0 will be remain 0 only. So only option left is you have to put 1 and 0, right? 1 to 0, 0 to 1. And for 1 to 1, for 1 to 1, you can have 0, 0 case, this is 1 to 1. If you have 0, 0, right, previous value is returned. And if you have 1, 0, that also will make sure that the next value is 1. In either case, for these inputs being present, if the previous value is 1, next value for sure will be 1. So that is R need to be 0 and S can be any of 0 and 1. So that is the case where we say what we say as cross 0. Is it clear? So the excitation table of SR flip-flop looks now something like this. So it is rereading of the truth table or characteristic table, okay, and putting it in a different manner, that if this is what is desired, if the circuit has to move, okay, from states, one state to another, and the states are represented by individual elements which are flip-flop, then to make certain changes happen, what should be present at the input? Okay. So this is looking at it from the reverse direction, right? Characteristic table, truth table, if this input is there, what will happen? What change will occur? And excitation table, if this change is to occur, what is to be present as input? Okay. So this is the way these two representations differ from each other. Okay. So this is for SR flip-flop. So we can see how it would be for other flip-flops. Okay. So for JK flip-flop, so again these transitions, all these 4 transitions are to be considered. So 0 to 0, right. So if 0, 0 is present, previous state will be written, and 0, 1 is there, okay. That also will make that the next state is 0 for previous state being 0, okay. So this is 0 cross, okay. And similarly 1, 1 like previous case, so 0, 0 and 1, 0, both the cases it is becoming, if the previous state was 1, so the next state becomes 1. So these two we can see, we can visualize from SR flip-flop excitation table, okay. Now coming to the other two cases. So for 0 to 1, in SR flip-flop it was only 1 and 0, okay. But in JK flip-flop, for 1, 1 input, we know the output toggles, okay. So if the previous value was 0, the next value will become 1, also for the case when input is 1, 1, right. So 1, 0, as well as 1 1. Why 1 1? Because the state toggles, 0 becomes 1. And why 1 0? Because that is how the things get set, similar to SR flip flop setting. Okay. So, these two cases we can see that a 0 to 1 transition is possible if that is the excitation at the JK flip flop input, right. So, we can put this as 1 cross, similar to what we did for SR flip flop truth table, excitation table. Similarly, for 1 to 0 transition, earlier it was only 0 1, now 1 1 is also possible because of this toggling part of the truth table in the JK flip flop. Okay. So, this becomes cross 1, right. So, this is how it differs, and what is its significance and other things. Okay. If we want to realize a circuit using SR flip flop or JK flip flop, okay, how these things will come up, that we shall explore in future classes. Okay. Now, for D flip flop, it is relatively straightforward. So, we know if the next state is 0, right, the input need to be present is 0. If the next state is for 0 to 0 cases 1, input need to be present is 1. Again from 1 to 0, since next state is 0, input need to be present is 0. 1 to 1, again input need to be present is 1. So, this is the excitation table of D flip flop. Okay. And for excitation table of the T flip flop, okay, so we have got 0 to 0. So, previous state is retained. So, this is 0. Okay. 0 to 1 toggling. Okay. So, input need to be 1. 1 to 0 again toggling. So, input need to be 1, and to 1 to 1 previous state is retained. So, input is to be 0. Fine. So, this is how excitation table is. Through excitation table we can represent different flip flops. Okay. Okay. Now, the excitation table, whatever we have seen there, we can put in the form of state transition diagram. This is another way of visualizing what is happening in a flip flop. Okay. So, for a particular flip flop, we have got two states, because it stores 1 bit information, state when it is the output is 1 and state when the output is 0. Okay. Transition means when the excitation comes at the input, so it is supposed to make it is now can make a transition. So, whether it will make a transition to next state as 1, or it will remain in the same state, that is 0 if the present state is 0. Okay. So, that is explained, that is visualized pictorially in the form of state transition diagram, through a diagram. Okay. So, if we look at the SR flip flop state transition diagram, so this is one state with value 0, right, and this is another state, current state described by 1. Okay. Now, when it is at state 0 and it receives the input 0 0, what will happen? It will remain in the same state. So, that is what is shown through this line. Okay. And this arrow mark will be there to show where it is. Okay. And if it is at state 0 and if it receives 0 1, if it receives 0 1, what will happen? It will stay at 0 only, isn't it, right. So, 0, it is remaining at 0 for the cases 0 0 and 0 1. So, you can see it from the excitation table, also from truth table we can in a inverted way you can figure it out, right. Now, it is at 0. So, 0 0 0 1 we have seen. If it receives a 1 0, what will happen? It will get set, it will become the next state will become 1, the state of the flip flop will become 1, right. So, it will move to 1. So, that is what is shown through this arrow over here. From 0 it is coming to 1, okay, and when the input presented is 1 0. Is it okay? Now, it is at state 1, it is state at 1, and it is receiving, whatever is allowed. Okay. Other than 1 1, everything is allowed, 0 0 1 0 and 0 1, right. So, these are the 3 things that are allowed for SR flip flop. So, if it receives 0 0, it will stay at 1 only. If it receives 1 1, okay, 1 0, it will remain at 1, right. And if it receives 0 1, then it goes back to state 0, it goes to state 0. Is it okay? So, for each of the stable state, right, for SR flip flop, okay, this bistable circuit, we can figure out for the allowable inputs, okay, what would be the next state, okay, and we can pictorially depict it through state transition diagram as you have seen here. Okay. So, for JK flip flop, again current state is 0, right. If it receives 0 and 1, it will stay here. If it receives 1 0, it will go there. If it receives 1 1, now 1 1 is also possible, then also it will go to 1. Okay. At 1 1, if it receives 0 0, it will stay here, 1 0, it will stay here, and if it receives 0 1, it will go to 0, and 1 1, it will go to, again it will toggle, so it will go to 0 similarly. Okay. For D flip flop, right, stable state 0, if it receives 0, it will stay here, if it receives 1, it will go to 1, if it is at 1, if it gets 1, it will stay there, if it is if it receives 0, it will come to 0. And for toggle flip flop, if it receives 0, then it will stay at 0, and if it receives 1, it will toggle, it will go to 1, and if at 1, if it receives 0, it will stay at 1, and if it receives 1, it will toggle and go to 0. Okay. This is the other way, other form of representation. Another representation through timing diagram, okay, in all these cases the delays and other things, okay, however small it might be, is not visible. Okay. All these representation that we have discussed so far. So, if we represent the flip flop, the transitions that are happening, okay, for a particular set of inputs, and rather all possible set of inputs, excitation. So, through timing diagram we can show it. Okay. So, that we shall discuss through some examples in some subsequent classes. Characteristic equation of a flip flop is a minimized representation of the next state by considering present input and present state. Excitation table shows in tabular form what as input is required to move the flip flop from one particular state to other. A don't care in excitation table indicates that specific transition will take place irrespective of the variable under consideration being 0 or 1, and the change in state of a flip flop for a specific input can be represented by state transition diagram. I mean, if you look for a pictorial description. Thank you.